Hi guys, and welcome to our first AP Chemistry flipped classroom video of the year. So today will be a short video. It's just a quick review of both dimensional analysis and significant figures. So if you're uncomfortable with the dimensional analysis system that I'm teaching, please feel free to come and talk to me and ask any questions, and we will go over anything. But the important thing to remember about dimensional analysis is that it's just a way of using conversion factors to solve problems. So we have to remember that any dimensional analysis problem, any conversion factor is really just 1. 12 inches equals 1 foot. So if we were to say 12 inches over 1 foot, that's a fraction that has the same thing on the top that it has on the bottom, because 12 inches equal 1 foot. So by our identity properties, we know that that's 1, and we can multiply anything by 1 and it stays the same thing. And so that's really how conversion factors work. We multiply by a conversion factor to change from one unit to another without changing the value of the quantity that we're measuring. So anytime we're doing a dimensional analysis problem, we want to think about where we're starting and where we want to go. So our first question, super easy, says how many milliliters are found in 12.52 gallons? So where are we starting with gallons? Where do we want to go to milliliters? And so we're going to go from gallons to milliliters. So we're going to start with our gallons here. And so we're going to put in the 12.52 gallons. And it's always important to start with as many significant figures as the problem gives you. So they gave us 12.52. We're going to use 12.52. We're not going to round anything. We're going to use that whole number. We also want to make sure anytime we're doing dimensional analysis that we always include the unit. So I have 12.52 gallons. So now I don't know a conversion factor from gallons to milliliters, but I do know a conversion factor from gallons to liters. And you might have to look these up sometimes. Most of the time, we're going to be using conversion factors that we know or conversion factors that we can calculate, like molar mass. Occasionally, we'll have to look them up. So if you had to look this up, you might find that 1 gallon equals 3.785 liters. So our next question is going to be, what do we need to put on the top and what do we need to put on the bottom? And so I always like to think of this as like a zipper. So we have gallons here. So I know that gallons need to go on the bottom, and then I'm going to come up. So I'm kind of going zipper, up, down, up, down. So on the diagonal, I want to put the unit that I currently have, because that'll put that underneath in the denominator, so that the gallons cancel out, because I'll have gallons divided by gallons. So I'm going to put gallons on the bottom. So I know that there's 1 gallon equals 3.785 liters. And so by putting that conversion factor in, I now know that my gallons are going to cancel out and I'm going to have liters. But liters weren't what I was trying to get to. I'm trying to get to milliliters. And so I need another conversion factor. And again, I'm trying to cancel out liters. So I know liters are going to go on the bottom of the next step. So I'm going to go ahead and put 1 liter down here in the bottom. And I want to get to milliliters. Well, I know that prefix milli means 1,000. So there are 1,000 milliliters in 1 liter. And when it comes to significant figures, we remember that this is a conversion factor within a system. And so this is an exact number. So even though that 1,000 has trailing zeros, we know that all of those zeros are significant. This number has infinite significant figures, so it's not going to affect our sig figs at the end. So now we can see that the gallons cancel out because I have gallons over gallons, and liters cancel out because I have liters over liters. And now my units are milliliters. So I'm actually done with this problem. I just have to multiply the numbers on the top and divide by the numbers on the bottom. And when I do that, I get 47,390 milliliters. Now, when you put that into your calculator, you'll see that it's not, the number that your calculator gives you is not 47,390 milliliters, but this number only has 4 significant figures, 12.52. And so my answer can only have 4 significant figures. So right here at this tens place, I had to round. And so this actually came out to like 47,388 milliliters and some change. So that 8 made the 9 round up. And this 0 being a trailing 0 is not a significant figure. So my answer of 47,390 milliliters has 4 significant figures. And we'll come back to significant figures in just a minute. So our next question is a little bit more chemistry based. It asks me how many atoms of oxygen are found in 32.1 grams of potassium chlorate. And so I know that I'm going to start with grams of potassium chlorate, and I want to get to atoms of oxygen. And you notice that now I not only need to keep track of units, but I also need to keep track of the thing being measured, because I'm trying to go from potassium chlorate to oxygen. We're not quite at stoichiometry yet because we're not talking about a reaction, but we do have to pay attention to our chemical names and what makes them up. So the first thing I need to figure out is, what is potassium chlorate? So I dig deep into that memory bank and I remember that chlorate is ClO3 with a charge of -1. So it's an 8, it's an oxyanion with a charge of -1. And I know that potassium has a charge of +1. So when I put those together, I'm going to get KClO3. So I'm trying to go from grams of potassium chlorate to atoms of oxygen. So I can't go straight from grams of potassium chlorate to atoms of oxygen. I know that I need to get, if I want to get to atoms, I need to get to moles. And if I want to get to moles from grams, then I need to figure out a molar mass. So I'm going to start out with my grams of potassium chlorate. And we have 32.1 grams of potassium chlorate. Whoops, that was not what I meant to do, but that's okay. So we have those 32.1 grams of potassium chlorate. And so in order to convert that to moles, I'm going to calculate the molar mass of potassium chlorate. And so I'm going to add up the mass of potassium, which is, I think I may have added up wrong, 39.098. And the mass of chlorine, which is 35.453, plus 3 times the mass of oxygen, which is 15.999, and we get 122.548. And so your teacher's going to have to redo her math here, because I did it incorrectly the first time here. So we're going to change this to 122.55 grams of potassium chlorate. And now we have moles of potassium chlorate, but we want atoms of oxygen. So I can't go from moles of potassium chlorate to atoms of oxygen. I'm going to go from moles of potassium chlorate to moles of oxygen. And I can see from this formula that for every 1 mole of potassium chlorate, I have 3 moles of oxygen. So that's my next conversion factor. And again, moles of potassium chlorate on the top, moles of potassium chlorate on the bottom in the next one. So here, what's going to go on the bottom here is moles of oxygen. And I'm trying to get to atoms of oxygen. So we're going to use Avogadro's number, which is that 6.022 times 10 to the 23rd atoms of oxygen per mole of oxygen. And so when we calculate all of this out, we get a number that is not the one that I have written here. I'll just really quickly fix that. So instead, we actually get this equals 4.73 times 10 to the 23rd atoms of oxygen. So here we started with 3 significant figures. All of these conversion factors, this one has 5 significant figures. The others are exact. So this answer is going to have 3 to match the least precise number that I began with. So our significant figures are going to convey our precision. So we're going to jump out of here and go to talk about significant figures really quickly. Okay, so significant figures. So we learned about significant figures in chemistry, and we'll just quickly review significant figures. So we use them to communicate how precise our measurement was. How precise was our instrument? All of our measured numbers and one estimated place are considered significant. You'll remember in class today, we said we always read one place past the graduations. So when we measure something on, say, a graduated cylinder, this graduated cylinder is marked in ones. And so we want to communicate to our audience that it was marked in ones. We're estimating the 10th place. So we would estimate this at, let's say, 53.8 milliliters. So we're always going to estimate that one place past the graduation. So by using the same conventions every time, we don't have to use the plus and minus designation. By using significant figures, we communicate that information to our audience. So we have some rules for counting sig figs. So when we're presented with a number, we're going to count the significant figures. So the easy one is that a non-zero integer is always significant. So 3,456 has 4 sig figs. When it comes, the rest of the rules have to do with zeros. So when we look at a leading zero, so this is a 0 on the left-hand end of a number or the Pacific side, then leading zeros never count. Leading, never. Okay, so 0.0486 has only 3 significant figures, the 4, the 8, and the 6. These 2 zeros are not significant in our term significant figures. Do they matter to the value of the number? Absolutely, but they are not considered significant figures. Okay, our next zero rule is the zeros that are always significant, and these are captive zeros. So if you have a zero that's between 2 significant figures, that zero is automatically a significant figure because we know that that's either that's a measured number. Okay, so 16.07, if I was measuring and I gave you 16.07 milliliters, you would know that that 0 is a measured number and the 7 is the estimated number. So this has 4 significant figures. And then our last zero rule, unfortunately, is a sometimes rule. So our trailing zeros, zeros on the right end of a number, they are significant only if the number contains a decimal point. So 9.300 has 4 significant figures. This last zero, this trailing zero right here, is significant because there's a decimal place here. This one as well. We could also talk about this zero in hundredths place as being a captive zero because it has significant figures on either side of it. So if I were to give you this number, you would know that this instrument that I used is graduated to the hundredths place and I estimated the thousandths place. So those are the rules for sig figs, whether something is or isn't a significant figure. But then we have to be able to apply those significant figures when we do mathematical calculations. So we'll do the easy rule first. And the easy rule is multiplication and division. And so in multiplication or division, the number of significant figures in our result always equals the number in the least precise measurement that was used in the calculation. So if we multiply 6.38 times 2.0, 6.38 has 3 significant figures, 2.0 has 2. So my answer can only have as many significant figures as my least precise measurement, and that's the one with the 2 significant figures. And so my answer only has 2 significant figures. So even though my calculator tells me 12.76, I'm going to round that to 13. The slightly more complicated mathematical operations, believe it or not, are addition and subtraction. So in addition and subtraction, we have to go back to remembering what do the SigFigs tell us. So in addition and subtraction, the number of decimal places in the result is the same as the number of decimal places in the least precise measurement. In fact, the last common place that they have is where you have to round. And so if we look at 6.8 plus 11.934, this 8 is significant. And this 9 and this 3 and this 4 are all significant. But we don't really know what's over here to the right of the 8. And so when we add this up and we get 18.734, we don't really know that this is a 3-4 because there could have been something else over here to the right of the 8. It could be a 2, it could be a 4. And if it was a 4, then that changes this number. So we don't really know that this is 3-4. And so we have to round it to 18.7. If we go back to thinking about what these tell us, if I am saying that I've added 6.8 milliliters of water to 11.934 milliliters of acid, I can only be sure of the 6.8, not 6.80 or 6.800. And so when we're adding or subtracting, we can only be as precise as our least precise number. And when we're adding and subtracting, our least precise number is really about decimal places. And so even though this number has 2 significant figures and this number has 5 significant figures, my answer is going to have 3 because it's not about the number of significant figures, but the placement. What place in the number are they? Okay, so that wraps up our quick review of significant figures and dimensional analysis. As always, if you have questions, let me know and we will practice in class. Look forward to seeing you.